Welcome to a deep dive into, well, this is a big one, Julian Schwinger's 1965 Nobel Lecture on relativistic quantum field theory.
Yeah, this isn't just some lecture,
Right.
It's Schwinger basically saying, hey, I just changed how we see the universe, and this is how.
Right, the Nobel Prize is like the ultimate physics victory lap, and we get to unpack his explanation, his snapshot of this game-changing theory at that exact moment. But before we go full-on physics nerd, can you give us the high-level view? What is relativistic quantum field theory?
At its core, it's about taking two of the most revolutionary ideas in physics, quantum mechanics, and Einstein's relativity, and smashing them together.
Oh boy, a clash of the titans. What happens when these two heavyweights collide?
Metaphorically, fireworks. You see, quantum mechanics is all about a world where things get fuzzy at the tiniest levels. It's about probabilities, not certainty. Like, imagine an electron, instead of it orbiting neatly like a planet, it's more like a cloud of maybe all around the nucleus.
So instead of saying the electron is here,
Yeah.
we're saying it might be here, or maybe even way over there.
Exactly. And then relativity enters the chat, shaking things up even more. It's like, hold on, even before and after depend on where you're standing, your frame of reference, especially for things happening across vast distances.
So two things happening at what looks like the same time to me might be totally out of sync for someone moving super fast relative to me.
You got it. Now, try blending that with the whole probability cloud thing from quantum mechanics. That's the brain-melting puzzle that relativistic quantum field theory tackles.
Sounds like trying to mix oil and water, honestly.
Not a bad comparison. And the way this theory pulls it off is a radical shift. It stops focusing on individual particles like electrons, and instead it says, what if everything is fundamentally about fields?
Fields, like magnetic fields? Are we all just living in some kind of invisible force field soup?
Kind of. Picture, say, an electron field. It's not something an electron makes, it just is. It's this fundamental thing existing everywhere all the time.
So not one electron, but an electron field that's just everywhere at once. My brain's starting to hurt.
It's a big concept for sure. And this field, it can be excited in different ways, and those little bursts of excitement, that's what we see as particles.
Hold on, excited. Is
Yeah.
it like a still pond and the electron's just a ripple on the surface? What's doing the rippling if everything's a field?
I like that visual. Think about what makes a ripple some kind of disturbance, right? Well, those disturbances, those are like our particles.
Okay, starting to get the picture here. But we're talking about quantum stuff.
Mm.
A and D relativity, shouldn't measurement be a part of this? Where does measuring things fit into this field-based universe?
Excellent point. Measurement in the quantum world is huge. It's what takes those probability clouds and forces them to give us a real
It's
answer.
like that whole observer effect thing, right? Like, until we look, it's all just maybe this, maybe that.
That's the gist. And relativistic quantum field theory takes that idea of measurement and plants it right into space-time. Schwinger even points out that there's this extravagantly large but finite number of ways we can measure things in this framework.
Extravagantly large, but finite. That sounds like a pretty important detail. Can you unpack that a bit? What does he mean, and why does it matter?
He's talking about that tightrope walk between what the math allows and what we can actually see in the real world. We can talk about infinite fields, but our measurements, those are limited. Our instruments, our observations, they aren't infinitely precise.
So it's like drawing a line on paper. We can imagine it going on forever, but any chunk we actually measure will have a definite length. Infinite potential, but finite interactions.
You've got it. That dance between the vastness of the theory and the limits of what we can observe, that's a big part of what makes relativistic quantum field theory so fascinating. And to get even deeper into that, we have to talk about one of the weirder implications of this whole thing.
Oh. Weirder how? I'm all ears. Lay it on me.
Antimatter.
Okay, now that's just taking us into sci-fi territory. Or is it, how does antimatter come out of this theory? Antimatter. Okay, now we're in the realm of Star Trek. But seriously, how does a theory that's supposed to describe the universe we see lead to something that seems straight out of science fiction?
It's not science fiction, believe me. Antimatter pops up naturally when you bring quantum mechanics and special relativity together. Like, one of the big things Schwinger was driving at was this idea that the universe, at its most fundamental level, it's got this beautiful symmetry to it.
Symmetry. Like how a butterfly's wings are mirror images. What's that got to do with antimatter?
Well, it's a different kind of symmetry, but yeah, the butterfly's a good visual. See, relativistic quantum field theory It basically says that if you flip the script, all matter became antimatter and you reversed everything in space-time, the actual structure of the theory would hold true.
Wait, slow down a second. You're saying if we had a mirror universe, all antimatter, the same laws of physics would still work?
That's the gist. This deep symmetry is all wrapped up in something called the TCP theorem, which Schwinger mentions in his lecture.
TCP theorem, got it. So it's like the universe has this hidden mirror image built into its DNA. But if that's true, shouldn't we see more antimatter around? Last time I checked, my car still runs on regular gas, not anti-gasoline.
Right. That's a great question, and it gets at one of the biggest mysteries physicists are still trying to crack.
Yeah.
Why is there so much more matter than antimatter if they were supposed to be created equally during the Big Bang? It's the matter-antimatter asymmetry problem.
Okay, yeah, that's going to need some explaining for sure. But let's bring this back to relativistic quantum field theory for a sec. We've got these fields, we've got particles, we've got this mind-blowing antimatter. How does the theory connect those fields to the actual particles we see around us?
Ah, million-dollar question. So back in the early days of quantum field theory, fields were often seen as this handy tool,
Mm.
like a way to describe particles without going totally bonkers,
Mm.
but not necessarily fundamental themselves.
So kind of like a mathematical shortcut.
In a way, yeah. Think about describing a wave on a pond. You could try to map out every single water molecule, its position, its speed.
Talk about information overload. I can't even imagine that spreadsheet.
Exactly. It's way more elegant to just describe the wave itself, its height, how fast it's moving, this wavelength. Those things are, like the fields in our theory, a more unified way of understanding how particles behave.
Gotcha. So instead of this messy jumble of individual particles, we get a more organized view through the lens of fields.
Right on. But here's the thing. Schwinger's work, especially in quantum electrodynamics, or QED for short.
QED, yeah, that's the one about how light and matter get along.
That's the one.
Yeah.
QED showed that the connection between fields and particles, it's way deeper than just a mathematical trick.
How so?
Well, one of QED's big reveals is that interactions between particles can actually change the properties of those particles. Schwinger uses this example of vacuum polarization to illustrate it.
Vacuum polarization. Wait, you mean even empty space can be polarized? Like what we think of as nothing is actually dot something.
You're catching on. In QED, empty space is more like a quantum foam. This crazy sea of virtual antiparticle pairs just popping in and out of existence constantly.
So it's like this bubbling, frothing soup of particles that are always appearing and disappearing, even when there's no real stuff there.
A very poetic way to put it. And now imagine dropping an electron with its negative charge into this quantum foam.
I bet that makes some waves. What happens?
You bet it does. Picture the electron surrounded by this cloud of virtual particles. The positively charged ones are drawn in, the negative ones are pushed away, and you get this sort of screening effect.
So the electron's trying to hide behind a shield made of these virtual particles.
In a way, yeah. And this shielding, it actually changes how we observe the electron's charge. From a distance, it appears weaker because of this effect.
So the charge we measure isn't its true charge. It's like a dressed-up charge that includes all those interactions with the vacuum.
Bingo. It's like the electron's wearing a disguise. And this whole dressing up of the electron's charge, that's called charge renormalization.
My head is officially spinning. But if I'm following, QED is all about electromagnetism. What about those other fundamental forces, like the strong force that holds the nucleus of an atom together?
Excellent question. And that's where things get even wilder. See, these ideas of vacuum polarization and charge renormalization, they work beautifully for electrons and photons. But when you try to apply them to the strong force,
It all falls apart.
not exactly falls apart, but it definitely hits a snag. The strong force, the one that binds those quarks together to make protons and neutrons, well, it's way stronger than electromagnetism, and it's got some quirks of its own.
Quirks, huh? How so?
Well, for starters, it doesn't weaken neatly with distance like electromagnetism. It actually gets stronger the farther apart the quarks get, like a really stubborn rubber band. And those quarks, they absolutely refuse to be alone. They always exist in groups.
So unlike the electron, which is cool hanging out solo, quarks are like the ultimate clingy friends.
That's one way to put it. And there's more. They got this weird rule where even though they have fractional electric charges, they always combine to make particles with whole number charges, like those protons and neutrons we talked about.
Okay, so we've got a force that acts super weird. We've got these inseparable quarks, and they're obsessed with having whole number charges when they're in a group. What did Schwinger have to say about all this? Did he have any answers, or was he just as stumped?
Stumped. Nah, Schwinger was never stumped. Intrigued, definitely.
Hmm.
He actually threw out this radical idea. Maybe there's a whole new kind of field out there, one that interacts super strongly with what we call nucleonic charge. That's the charge carried by protons and neutrons.
A new kind of field. So not electromagnetic, but something else entirely. Did he have a name for it?
He didn't give it a specific name, but he suggested this new field could be the key to understanding the strong force and all those quirky quark shenanigans. He proposed that this field might be what's holding protons together and making them stable, just like QED explained the electron's stability.
So just like the electron hangs out with the electromagnetic field to stay stable, protons might be snuggling up to this new, mysterious field to keep themselves from flying apart.
Exactly. It was a bold claim, and it raises a ton of questions.
Like what? Spill the tea.
Well, if this field is real, what are its properties? How does it interact with the other fields we know about? Could it even lead to brand new, even more fundamental building blocks of the universe? These are the kinds of questions Schwinger's work opened up.
Whoa, talk about a cliffhanger. But before we spiral down that rabbit hole, let's make sure we tie this back to our main event, Schwinger's Nobel Lecture. How does this idea of a whole new field connect back to his lecture, and why was it such a big deal back then? So we've got this brand new field, potentially upending everything we thought we knew about the strong force. It's a pretty bold move, even for a Nobel Prize winner. How did Schwinger bring this back to his lecture? It's not like he had concrete proof just yet, right?
You're right. It was definitely a prediction, a glimpse into the future of physics. But Schwinger, he was always a few steps ahead. He connected this whole idea back to a core part of his work, something the Nobel Committee definitely recognized. Remember those phenomenological fields we were talking about?
Yeah, those effective fields that help us describe how composite particles act without getting bogged down in the nitty-gritty of every single quark inside them.
Exactly. Schwinger argued that even if we didn't fully understand this new field or how quarks danced around in it, we could still learn a lot by studying the bigger picture, how those composite particles, those phenomenological fields, actually behave. He thought that instead of getting lost in the weeds, we could uncover the secrets of the strong force by looking for patterns in these larger systems.
So instead of trying to track every single bee in a hive, we can watch how the entire hive operates as a unit. We still learn a lot, even without knowing every detail about each individual bee.
Perfect analogy. And Schwinger was convinced this approach, this focus on phenomenological fields, could revolutionize our understanding of the strong force, just like QED did for electromagnetism. He saw it as the bridge between these abstract quantum fields and the tangible world of particles and forces that we actually experience.
Okay, so that's how he proposed tackling this massive problem. But why was it such a big deal back then?
Because it was a whole new way of thinking about physics, a complete paradigm shift. Remember that quote from Keats that Schwinger used, the one about Cortez staring out at the Pacific? He was comparing the state of physics at that time to the awe those explorers must have felt when they first saw this massive, unexplored ocean.
Okay, so the Pacific Ocean is like all the stuff we don't know about the universe, all those mysteries just waiting to be uncovered.
Exactly.
Mhm.
Schwinger saw his work, and the work of all those physicists wrestling with relativistic quantum field theory, as the first steps on a very long journey. Just like those explorers standing on the edge of a continent, staring out at this vast, seemingly endless sea, physicists were standing at the edge of a brand new understanding of reality, with a whole universe of possibilities stretching out before them.
That's both incredibly exciting and kind of terrifying at the same time, you know? Exciting because who knows what we'll discover, but also kind of terrifying because it means questioning literally everything we thought we knew about how the world works.
You hit the nail on the head. And that's the beauty of this theory, the beauty of fundamental physics in general. It can totally upend our perspective. We spend centuries thinking about matter as these tiny solid particles, and then relativistic quantum field theory comes along and says, hey, what if those particles are just ripples on a much deeper level?
Ripples on a sea of fields that are constantly interacting and creating this incredible, complex universe that we're all just floating in, I guess. Talk about a mind-blowing concept. But if we're really at the edge of this vast, unknown ocean, what are we supposed to do with this knowledge? Where do we even go from here?
We dive in, we explore, we never stop asking questions. If the particles we see are just ripples on the surface, what's creating those ripples? What lies beneath? What are the properties of these fundamental fields? How do they all interact to create this incredible diversity of particles and forces we see in the universe? These are the questions that physicists are still grappling with today, questions that Schwinger's work allowed us to even ask in the first place.
And questions for all of you listening to ponder as well. If the particles we observe aren't the fundamental building blocks of reality, what does that say about the nature of the universe? What other mysteries are waiting to be unraveled? Something to think about as we wrap up this deep dive into the heart of relativistic quantum field theory. Thanks for joining us.